Hello, my name is Luke and welcome to this PyTorch tutorial series. In this video, we're looking at part 2 of section 12. As per usual, all the code is available in my PyTorch tutorial series GitHub. So section 12 today and PyTorch 2, autoregressive and RNN. So in the previous video, in the previous section, we looked at what sequential data was, what time series data was, and looked at a basic example of using a simple MLP to predict some temperature and rainfall data. And we saw how if we just do a one-step prediction, we get sort of very noisy, not very good predictions. But if we were to feed predictions back into the model, we get a slightly less noisy predictions and predictions that sort of follow the patterns a bit better for our weather data. But as I left off in that previous video, we said, well, with that simple MLP with a fixed length of, say, 14 days of that weather data, we don't, have much to predict the next day on, only 14 days. Maybe we want to predict off 30 days, 60 days, or maybe we have are restricted in some way by the number of days we can predict for one situation, and maybe another situation we have more data or a longer sequence of data input that we want to predict from. So how can we handle that varying input of information into our network? So instead of having that fixed input, how can we have some way of having a varying input? So let's unpack that and just draw out what I'm talking about. So if we imagine we have our sequence of days again, so day 1, day 2, day 3, day 4, day 5. So I'll just have 5 days for now. And we use 14 days. So we're trying to predict the next day from the previous 14 days. Let's just use 4 days as an example here. So I feed the previous 4 days of, say, the maximum temperature into my neural network or my MLP. And I'm trying to predict the 5th day. And if we were to then make that prediction and then feed that prediction into our network, or even if we were just trying to predict the 6th day based on these days, right? So 6th day. Now we're predicting, because we have a fixed length input, we're going to have to drop this first day because we only can take 4 days as an input. An MLP with our linear layer has to have a fixed number of days. But what we really want is to take all of the previous days that we have into consideration when making a prediction for the next day. So what can we do here? Well, like I said, the problem really is that our neural networks have to have, linear layers have to have a fixed size input. You could potentially use something like convolutions, but even then with our convolutions, can they have a receptive field of my output being the entire input? I'm going to have many layers. You're probably going to have to do something like an average or sum pooling at some point to combine everything together to have a fixed size output for your linear layer that predicts at the end or something like that. So you can kind of solve it with that, but you still might run into problems. So what we might want to do is, say I'm predicting my 6th day from these 4 days here. And let's imagine, we have more days, maybe day 0, -1 previous days, right? What we want to do, what we could do, is we could have some way to turn all this previous data, all these previous days, into some fixed length vector or fixed length summary of all the previous days. And because it's a fixed length, we can put that into our network. Our network can assume, or assume that's going to get some additional fixed length data that's going to go into our network so we can predict the next day. So we want to somehow create like a summary almost of all the previous data into a fixed size vector. And then we provide that to our network. And then, we move on to the next day and we create a new summary of all the previous days, feed that into our network, right? So how are we going to create the summary? Well, simply we're going to get the network, our MLP here, to do it, to produce its own summary. So MLP here, right, is going to take in days 2, 3, 4, 5 and create a summary based on those days. But if we imagine instead of 2, 3, 4, 5, to create this summary here, sorry, let me just undo that, keep that. To create this summary here, well, we just use the same network again. So it's not a different network, it's the same network. So imagine we had -2 here as well. With that, to our same MLP, produce the summary, and it's also going to get a summary as well from the MLP, the previous time steps. Right, and at the very start, we'll initialize this all to just zeros. So it's just all going to be zeros. So the MLP will take in the start sequence, it will then generate a prediction and also a summary of its input. And it's going to pass it to itself in the next time step. So if I draw this out a bit neater, we can see what's going to happen here. So I'm just going to write the numbers out. Imagine they're in the boxes. This is just the data at these different days. Let's say we take in these 4 days into our MLP. And we get a summary. Again, it's going to start off at all zeros into our MLP. And we'll do our prediction for day 5. And then it's also going to create another little summary. It's not going to be zeros at this point. And then we have the same MLP. And it's going to take in that previous summary and also days 1 to 5. And it's going to try and predict day 6. So imagine we have that going over and over again. I'll draw it out one more time. So this is going to produce another summary. It's going to go into the MLP again. And it's going to take days 3, 4, 5, 6 in as well. And it's going to predict day 7. So here you can see this MLP in this third step here. It takes in 3, 4, 5 as input, but also it takes into as an input this summary. This summary comes from a network that had 1, 2, I've kind of skipped 2 here, 1, 3, 4, 5, right, as an input. So it's produced that summary from these days, but it's also got this summary as an input, and this summary is created by the network when it had the first days in as an input. So this summary here has information about days from all these days here, and this MLP also additionally gets in day 6. So this prediction here actually takes into account all these days as input, even though the MLP at any one point in time only saw the raw 4 days as an input. Yeah, I've skipped day 2. Whoops. So even though our MLP has a fixed length summary, so that's fixed length input of the days and a fixed length summary, it can make decisions if we structure it in this way based on all the previous data. So we can keep going on this sequence forever. And theoretically, at least, MLP at any one time step is going to be able to make predictions based on all the previous data that it has seen in this sequence. And we call this sort of architecture and training structure or training regime a recurrent neural network. So that's what this little diagram here is showing. Recurrent because we're passing the same output and an output into our network over and over and over again in a recurrent way, like a recurrent function, to make subsequent predictions. So here's a sort of diagram. We pass our output back in. If you sort of unfold that, what that looks like is we have that's our sort of summary or buffer into our network and takes the input in, predicts the output, and then produces the summary again. So you might think, well, how do we train the summary? Well, we don't really need to do anything. We just train our network as per usual. And the assumption is that, well, my MLP at this sort of time step here might want to use information that it didn't get directly as an input. So we're going to get some gradients from our network backpropagating. So we're actually going to backpropagate through the summary into the network at this time step. And I'll say, hey, me at the previous time step, I'd actually like to see some information about day 1 and maybe even day 0. And so it can backpropagate through this way as well. Or it could backpropagate from the output of the prediction here into this MLP and say, hey, I want some information about day 0. So it's going to train purely just through our normal prediction like we did before, but we're going to backpropagate now through time the backpropagation through time, so that this sort of summary, or the MLP, learns to produce a summary of potentially useful information that it might think is useful for itself in the future in subsequent steps. Okay, so let's have a look at how we implement that. So we're using 30 days as well. So we're going to have 14 days as input as well, but we're now going to have that summary that our network produces to feed back to itself. So 14 days, and we're going to slide along one day at a time and make predictions. So again, we have our weather and temperature, or our rainfall and temperature data. So our recurrent neural network here, pretty similar to before, but you can see that it takes in as input that summary. I'm calling that buffer input. And so it gets some buffer from the previous time steps. And you can see that we are concatenating that. We're concatenating that at the start here before RNN cat, which is, this linear layer here as our input. So we pass the days through this MLP here, and then we concatenate the output of that little MLP with that summary buffer, and we pass it through a linear layer and the res blocks like we had before. And then we have our predicted output. So FC out here is the prediction for the temperature and rainfall. And we also have another linear layer that's going to produce the buffer for the next time step, so the new summary. Note that we're using a tanh activation function here. The reason we're doing that is to sort of bound the magnitude of the summary buffer. If we just leave it unbounded, so tanh will restrict it between -1 and 1. If we don't do that, the network can grow the magnitude of that buffer to be quite large, as it's trying to shove a lot of information into it, and that magnitude get quite large, and it could explode in magnitude and lead to unstable training. So we're just restricting that using the tanh to stabilize training a bit. So everything else is pretty similar. The only difference here is that you can see I'm already training this. We have this new buffer in our training regime. So again, everything else is pretty much the same except for this buffer now. As I mentioned, we're going to initialize it with zeros. So we're going to still pick some random point in our training data, and we're only going to use 30 days, but we're going to be able to make a prediction of all the previous days because of that summary we're providing ourselves. So we need to initialize the buffer to something. So we're going to initialize it to zeros, and we feed that into our network as well as the actual days. And we're going to predict the next day, temperature and rainfall. And we also produce the buffer. The buffer, that prediction will go back into the network again, as we saw by passing in as input our previous predictions. We can become robust to errors in our predictions. But as I said, we're sort of losing any information about previous days beyond our input. So by passing the buffer in as well, we're getting to see even further back in time. So that buffer here gets produced by the network, and the next time step, that obviously is going to be the input. We can also do this if you want without feeding the predictions back in, though I'm feeding them back in here. So if we just sort of shift this along without putting our own predictions in, you can put in the real predictions, also the real ground truths every time step, and that'll work too. But like I said, as we saw, feeding the predictions in during training can help become robust to errors. But again, it's always going to see the original 14 days because it's producing that summary at all at every time step. So this is almost done training. I'll just pause here and get back when that's done. All right, so that's finished training. You can see our loss has gone down slowly and converged. So now once we do our test rollouts, we're going to do a similar thing to what we did with training. We're going to initialize a buffer with zeros and input our days, and then roll out, putting the predictions back in as an input and predicting subsequent days from that. But again, we have that buffer as an input as well, which provides us with a summary, provides our network with a summary of all the previous days. Another thing we could do, I'm not doing here, is actually run this with the real ground truth data for a number of steps before we start feeding predictions back in. So we run this with the actual ground truth data. So our network only takes 14 days as an input, but say we want to actually run this for 30 days before we start making predictions and feeding them back in. So what we can do is we can initialize our buffer, feed in the ground truth data, have our buffer being produced and fed back into our network. And then when we want to start making predictions and feeding them back in, we then take that buffer, instead of using the one that was initialized to zeros, having that as an input as our summary of all the previous days, and then start feeding predictions back in to itself. And we'll see that in a subsequent video with code there. So if we have a look at our predictions now, you can see it's a bit less noisy again compared to the previous video where we fed the predictions back in. It's still very noisy. We're getting these sort of negative predictions for rainfall as well. You can see that's kind of gone away. And it sort of looks a bit more realistic. And you can see for our daily maximum temperature, we do get this nice drop in temperature around about where it should be. Though you can see we still get this, it's not quite in the right location. And it doesn't really come back up again later on. So there's still some room for improvement in our actual predictions for the temperature. But because, again, it can kind of see the pattern from the previous days, it knows that after a while the temperature should drop. Right? That is something that all of these previous methods we saw, it didn't really drop at the right time, or it didn't really drop at all. Look at this one where we didn't feed predictions back in. But because we have that buffer summary, our network should know that eventually after some period of time, the temperature should drop. And we do see that here, but it's not quite in the right location just yet. And it doesn't go back up again, potentially because we're trying to predict much further into the future over more time steps than we ever did during training. So maybe if we run it with more than 30 days training, we get a better result as well. But again, that's going to take even longer. You'll notice that each of these subsequent trainings takes longer and longer because every sort of propagation we do requires we do sort of 15 time steps before we do one back propagation. So it's going to be quite a lot slower. So I thought I'd just show you what I meant by sort of pre-populating that buffer summary. So as well, I've made a copy here, and I'll include this in the repo as well. In case you don't want to train with its own predictions, you want to use ground truths at every step during training. So I don't initialize that sequential block. I create it at every step in that loop. Again, just shifting it along to get that window of 14 days. So it always gets the ground truth as input. And again, we pass the buffer to itself. We initialize the buffer to zeros still, but we don't concatenate the predictions onto that sequential input block. We always use the ground truth there, and that buffer will provide the summary of the previous days as well. For the evaluation, if we want to sort of pre-populate that buffer, so even though our network only takes in 14 days, we can sort of use a longer sequence, say 30 days, to pre-populate that buffer and make predictions based on, say, the 30 days with that buffer summary. So we initialize the buffer to zeros, but we always provide it with the ground truth blocks and pass the buffer to itself. And we're doing 30 days here. I've just hard coded, and we're taking the predictions from that as well, but it's going to have the ground truth at every time step as well as the buffer. Then if we want to start feeding predictions back into itself, say we've only got the last 30 days, we want to now predict into the future, what we can do is we now feed the predictions back into itself, and we use the buffer from this stage. We don't really initialize it. We use the buffer from that, which has the sort of summary of those 30 days. And we predict and feed those predictions back in as an input, and we recreate that buffer. So I've only trained this network for about 100 epochs, but you can see that it does reasonably well. You can see for the first 30 days of the temperature prediction, it's pretty dead on. That's what you would expect. We're only ever actually predicting one day into the future. And then after the 30 days, it kind of drops a bit, starts to diverge from the ground truth. It drops and it kind of goes back up again. You trained it for longer, the same amount of time, probably be a bit better, but you can just see that it kind of tries to follow a pattern at least. The MSE value is pretty low though, but it's not a really good indicator of performance. So that's just how you would do that. You could actually do this for our model that was trained with feeding its errors back into itself. See if this works. So there you go, that's actually a bit better. So we're doing the same thing here, feeding the first 30 days in and then predicting further from that. So you can see it does drop a bit nicer and kind of tries to go back up. But again, we're only training with this short 30-day sequence, so to expect it to be able to predict really far into the future after only training for 30 days is maybe a bit of a stretch there. But yeah, it's performing a lot better now if we compare back to our previous ones where it kind of followed a pattern but didn't really. Now you can sort of more definitely see the pattern of it temperature dropping and starting to come up there. So it has that buffer summary of all the previous days. So what we're going to try and look at in the next video is ways to improve this recurrent architecture. So even though we said theoretically that summary buffer should contain information of all the previous time steps, in practice, the network really struggles to be able to do that, especially for really long sequences. We're feeding the buffer back into itself at every time step, and one such problem is very similar to the vanishing gradients with a deep neural network. So if we remember back to our residual and skip connections or very deep neural networks, we're trying to solve the problem of vanishing gradients, right, with a very deep network, and we're trying to backpropagate through it. We're doing many, many multiplications of the weights, which are all very small values, less than 0, so the magnitude of the gradient disappears before it gets to the really early layers, so those ones don't train too much. Similar sort of thing is going on with our recurrent neural networks. If you remember, that summary buffer is trained by backpropagating through time. For this sequence, we only got 3 steps here, and even our one in our code is only 30. But for much longer sequences, the sort of information from maybe this time step that sort of backpropagates all the way to the network at this time step gets weaker the longer the sequence is, and eventually might disappear altogether. We've also got that tan H that we're trying to use to stabilize the training by restricting the magnitude of that so it doesn't explode as well. That again is going to exacerbate the problem of the vanishing gradients as well. So we've got that problem. Also, because we've got this fixed size input that is restricted with the tan H, it can't fit as much information into that summary buffer. It also doesn't really have a way of sort of making fine changes or deliberate changes to what information is in the buffer. It really can only add information into it. And so, it also impacts how much information it can actually put into the buffer and how far that can propagate into the future. So in the next video and next code example, we're going to see a different architecture to hopefully solve some of those problems. So I'll see you in the next one.